Have a quiz?
No.
Really? All right.
We just covered reverse Polish notation.
Mm-hmm. Really? All right. What was the homework assignment?
Some.
Oh, right. How did that go?
Not bad.
Easy?
Most of it do.
Huh?
I missed that class. About the angel thing. Was it just supposed to add everything that was in the stack to...
Together and then push the result back on the stack.
Okay.
I suppose if you forgot to push the thing back onto the stack, you'll still get better than a 0. Since all you have to do is say this dot stack, this dot the stack dot push. It's one line of code. All right, so we need to write a sum. So where do we want to put that? We'll put that here. So if they put in a sum, what are we going to do? Well, we're going to say int sum is equal to 0. And we're going to say while this dot the stack dot is empty, while it's not empty, sum plus equals this dot the stack dot pop, this dot the stack dot push sum. So the whole thing. Does that look right? So for most of you, the assignment took 5 minutes or so. So common problems folks ran into is you wanted to use what we did for like add, where we popped 2 things off the stack. You kind of use this as your model. So what was happening inside of here is you were saying, so I'm lost. Yeah. What you were doing in here is you were saying sum is equal to sum plus this dot the stack dot pop plus this dot the stack dot pop, or something along those lines. Maybe you were storing that in 2 variables and then adding them together. But in any case, so you're late because you were smoking?
Oh.
You were definitely smoking.
Oh, well, I did on the way here.
You just woke up.
You just reek of smoke.
I was late because, you know, the whole brushing snow off the car with one arm.
You're just going to keep using this arm as a handicap, aren't you?
Yeah, I am.
He did text me. So at least there was that. You can still text with one arm.
I use my mic in my car.
So,
It's Siri.
in any case, a lot of people were going through like this and popping twice in the loop, which was then the very last time through the loop, you were actually getting a null pointer exception because you were popping off the empty stack, right? Okay, because when you ask this question, is the stack empty? All you know is there's at least one more thing in there. You're not guaranteed that there's going to be 2. In fact, you're pretty much guaranteed that there won't be 2 your very last time through. Does that make sense? So you can't pop twice each time through there. So you create a single variable called sum, and you accumulate your sum inside of that by popping one element, the element that you know for a fact must be in there if you're inside this loop. So that was the most common mistake people were running into. And then, you know, some people didn't push it back onto the stack, not the end of the world, but definitely do this because one of the, that's that one line. So we accumulated our sum inside of this variable, then we took the sum, put it back on the stack. So what's on the stack is the result of all the math we just did. That's kind of the thing with reverse Polish calculators, is it should always hold on the stack your last value. Okay? So we can go test this. So we can say 1, 2, 3, 4, then we'll do show, showing us the stack, and then we'll say sum. and then we'll do show, and that shows us the sum.
We keep adding to it. See if yours.
What do you want me to do?
Oh, one issue I noticed.
You want me to put a 5 in there? So now we have show,
Yeah.
5, 10. And I can say plus, and I can say show, we got our 15. What if I sum up just one number? So 15, went through the loop once, right? All right, so make pretty good sense. All right, what else might our calculator do?
Remove the last thing in case you screwed up.
Remove the last thing in case you screwed up. Okay, so for instance, right now I have what, just a 15 in there. So I do a 5, so I have a 5 and a 15. So if I do plus and do that, now I have the 20, but I've lost the 15 and the 5.
Question. If you subtraction, which one is it subtracting from the stack? Top one or-
So if I do 5, so our stack looks like that, then I say minus, it's taking this number, subtracting from it this number.
Okay.
So always the last thing that you had on the stack is your starting point. So that's 5 minus 20.
So is it supposed to be 5 minus 20 or 20 minus 5?
I don't remember.
Okay.
But how ours currently works is like that.
Okay, because I found an easy solution for that. Subtraction, you just flip num1 and num2 in the actual subtraction, and it works right.
Yeah, I mean, it's a trivial change.
Yeah.
It's a trivial change to it, but I'm just staying consistent and saying whatever's the last thing, that's what's on the left-hand side of your operator. To be honest, I don't remember how the Hewlett-Packard. Let's see real quick. There's probably an emulator out there. P.
Museum of HP.
I want one that launches. Oh, there's one for the App Store. I want here. I want that. I want. Let's see. Let's see if there's a Flash one. Is that this one?
Didn't you just click on that one?
Thought so.
I know they have them on the App Store.
Say this again.
I know they have them on the App Store.
The App Store.
Are you just looking for like reverse Polish calculators?
Yeah. Or an H. Here, I got to spell calculator right.
RPN calc.
Is
Reverse
it?
Polish calc.
I want a free. I want a free one.
I know that stuff's
Just
in
looking
the
at
man.
iPhones.
It's like extra required files and stuff. All right. Well, I don't. Did somebody check reverse Polish, how it's supposed to work? Does it do the? If I do 10 and I do 5 and I say minus, does it do 5 minus 10 or 10 minus 5? Ours currently works as it does 5 minus 10, so it should give you negative 5.
That's right.
Negative 5? All right, so mine works correctly? All right, perfect. You're wrong.
I didn't.
Ha!
What? I asked which way it worked,
And I told you it works just like mine.
and I believed you.
All right, so what else might our calculator do? What about average? So let's say we have a big stack of numbers, and we want to take the average of that. Now, should that consume our stack of numbers? We could certainly make an argument that it would. But couldn't we also make an argument that if I have 10 numbers and I want to get the average and push the average back onto the stack, it won't consume those numbers? So let's write that. So we want to have a function called average.
Can you just run sum and every time it runs, it adds to a counter, and then you divide the sum by the counter?
You can, but then you've also destroyed your...
Well, before you divide sum by counter,
You-
you just push sum back onto the stack.
your stuff is gone. You've taken it off the stack. You've consumed your stack.
The counter is not related to it. The counter is separate.
Right, but sum,
Yeah, all your...
when we pop it off the stack,
Yeah.
we're consuming the stack. That removes it off the stack. So we're summing every single time we're removing one of our numbers from the stack. Then in the end, we're just pushing this back on. So instead of pushing on the sum, you're saying I want to push on the sum divided by a count, which is fine. So that'll give me the average. But what it doesn't do is it doesn't leave the numbers I originally had in on the stack.
Okay, that's what you want.
Yeah, I don't want to consume the stack. So if I have 10 numbers on there, ultimately I want my stack to have 11 numbers. The 10 original plus the average of those 10. That make sense? All right, so average is summing up a bunch of numbers and then dividing it by the number of numbers. Correct? Do we have a count in our stack? Okay, that's fine. So we're going to say int sum is equal to 0, int count is equal to 0, while not this dot the stack dot is empty. All right, so we'll keep going through our stack over and over and over again, looking for a number. We're going to keep popping the number off, and we'll keep adding it to our sum. So we'll say sum plus equals this dot the stack dot pop, just like we did before. And then we'll also say count plus plus. And at the very end, we're going to say this dot the stack dot push sum divided by count. And we'll say it's going to be the integer average. So we'll do integer division here. Because actually technically we can put whatever we want on our stack, but it'll truncate because our stack only knows how to hold ints. This is this is an integer only reverse Polish calculator. So what this does is it goes through, keeps popping stuff off of our stack, adding it to our sum, ultimately pushes sum divided by the number of elements back onto the stack, which is the average. But what we've lost, so if we just go ahead and run this real quick, what we've lost is all of those numbers. So I'll say 1, 2, 3, 4, 5, 6, 7. We'll do shows us our stack. Then I'll say AVG, and I'll do show, and we see we have an average of 4, but the rest of our stack is consumed. It's gone. I want this to now show 1, 2, 3, 4, 5, 6, 7, 4. 4 being the average. Okay, so I need to make sure these guys get back onto the stack. How do I do that? Make a temporary stack. Okay, so as I am taking these things off, so I'm going to say int val, and right here I'll say val gets the value, this dot stack dot pop. So I'll go ahead and grab the value from my stack and store it inside of val, and I will add val into sum. But now I want to have a temporary stack. Oh, I already have a val. Let's call this guy temp num. Temp num. Temp num. All right. So now you want to create a temporary stack. So maybe we call this guy stack temp stack is equal to new stack. And then every single time we pop something off the regular stack, then we're going to say temp stack dot push temp num. So we'll push it onto our other stack. Okay? So think about how this is going to work. If we have 1, 2, 3, 4, 5, 6, 7 over here, 7 was the last number. When we pop 7 off, we're going to push it over here. 6, 5, 4, 3, 2, 1. Then if we go back through and we pop off this stack and push them back onto the other, it's back into the original order. Okay? So we'll pop it off the stack, store it in temp num, add temp num to our running total, push temp num back onto our temporary stack, increment our count. Now down here, since we want our average to be the very last thing, we first need to go back through and push everything from temp stack back onto the stack. So we'll say while temp stack is not empty, this dot the stack dot push temp stack dot pop. All right, so we'll take all of those numbers that we had popped off of the stack and we'll pop them off of temp stack and put them back into the stack. And then we'll show our, then we'll push our average. So let's look at this. All right, so if I do show, it shows my stack, but remember our stack is upside down, so this is 7, 6, 5, 4, 3, 2, 1. Then we're going to type in average, and then we'll show there's our average, and here's the stack. Make sense? And then we can take the average again. Our average stayed the same. Take the average again, average again, average again. How is it still 4? Oh, because I'm just adding 4, so I'm going to keep getting it. It's a math thing, right? Ha! No, it's no longer 4. All right. Does that make sense? Now, would it be helpful to remove an element from the stack?
Yeah.
Kind of like a delete that basically just pops something off the stack into oblivion. So maybe we see the average, but we're not interested in the average. We don't want that to be part of the future stuff, right? So maybe we add a command for delete.
Remove flags.
And what's delete going to do? It's going to do this dot the stack dot pop and do nothing with the value. I can run this. There's our show, del, there's our show, del, there's our show, avg, there's our show, del. Make sense? So far, it's a pretty legit calculator.
Well, calculators have the delete buttons.
Huh?
Calculators don't have that button.
I think that they do on reverse Polish calculators. I'm almost positive. Yeah, here was the calculator that I used to have. Yeah, drop the back button.
Did it come with its own briefcase?
Well, that's like the same size of the normal graphing calculator, isn't it?
So it just came with a pencil protector.
No, it actually came with like a, yeah, here's the case. It came with like a pretty nice HP case.
It's legit.
This was like a crazy expensive calculator. I think they were like $600 or something. They were really, really expensive.
Years ago was that?
94-ish, 95.
Like $1,000 calculator today.
Well, no, this is probably a. If this calculator existed today, it would probably be $100.
Yeah. Yeah, no, I meant like the amount though, like $600 back then. That's $1,000.
What was cool about it
Yeah,
back
it's
then?
about
Yeah.
Huh?
It's about $1,000 today in today's money.
Oh,
Yeah,
I got it.
that's
I understand what you're saying. Yeah, what was cool about it is you can do symbolic algebra with it. So before they had like the TI-89 and the TI-92. Have you ever seen a TI-92 graphing calculator? She looks like a laptop. So it came out before the 89 did. So TI-92.
What the fuck? Whoa.
I had one of these. It was awesome. This thing, it did symbolic, full symbolic algebra and integration. So like when you were doing your math test or something like that, you would just plug in the answer or plug in the question, and it would give you the answer. Then you can reverse engineer your work. So yeah,
That's probably why they don't allow it.
well, no. So this one is obvious, right? If the TI-92 too, I had the original. So if you if you have this in class, if you're hauling a laptop as your calculator, does it actually show one with somebody's hand on it? It's probably 3 times wider than a normal. Yeah, something like that. Maybe 4. But yeah, look at the stuff you could do in it. See this?
Jesus.
Isn't that sick? As a calculator. Well, so people were, you'd get caught using something like this. People, because the teacher would know. But you get the TI-89. Okay, looks just like a normal calculator, but has all that symbolic crap. So if your graphing calculator can do a symbolic integration, then you have one of these cool ones that are technically not allowed on the. Oh, so there used to be games. So Mario Brothers, Super Mario Brothers 3 and the TI-89. So this is what I did when I was in school. I would sit there and write programs. I didn't write Mario, but I would write programs for my graphing calculator. I had like a little rocket launcher thing where you would you had to like take off and land on a planet. So you'd start the game and it would take off, and then planets where you would get a random planet you'd land on, and the planet was sometimes moving and stuff, and you had to like adjust the thrust as you were coming down so you wouldn't crash into the planet. Kind of like a moon lander. That was back kind of when we were interested in the moon lander. Okay. So, and Final Fantasy? Legit.
I'm 1 or 2.
Do we have Zelda?
You guys ever get any work done in the class?
Doom.
And me and one of my nerd buddies, we wrote for our graphing calculator, Super Mario 68K. We wrote the name of our game for our calculator was called Ghettos and Gangsters. It was like an RPG drug dealing type game.
Grand Theft Auto, the first iteration.
So, in any case, kind of cool stuff. All right, so we have a fairly functional calculator now. All right, so that's a stack. Now, we want to now take our stack data structure. So, first of all, we were able to write something pretty functional. This is a program that you could actually use for something, right? You could pretty easily turn it into something that supports decimal numbers and things like that. You would have to change the nature of your stack so that your stack now didn't hard code to int. Maybe your stack took the number in as a string and then determined what kind of value it was. Kind of makes sense? So as an example, let's say that, just real quick, we'll just do this in driver. Let's say we have a method.
Couldn't we just hard code it to doubles?
Well, we could, but what if you wanted your thing to support other stuff like Booleans and things like that? But so you could hard code it to doubles, but then when are you going to do integer math? When's it appropriate to do integer math versus decimal math, real number math? So let's just do this. We'll say static void display type. And this guy will take a string as a parameter. And for this little example, since I don't want to spend too much time on it, let's say that this guy, the two types it supports is ints and doubles. Okay, ints and floats, whatever you choose your poison. Okay, but it's always going to come in as a string. Now, how do we determine whether this string is a double or a int? And we can assume it's an actual number. What's the difference between a double and an int? We want to have a decimal point. So basically, we want to search for a decimal point. How do we search for a decimal point? How could we ask the question, does S have a decimal point in it? And again, I'm assuming S is a legal number. So it's either 3.14 or it's 3, something like that. We don't have to worry about there being multiple decimal points in there or something. So how do I ask the question, does S have a decimal point? Have we talked about contains? Not here. Using only the tools that we've dealt with in here.
Make it a char array and make it index of -1 for a decimal.
Okay, why do I need to turn it into an array?
You can use their index of for a string.
Yeah, I can use index of. So I could say if S dot index of decimal point is not equal to -1, then system.out.println double, else system.out.println int. So this would be a very generic, very simple type inference engine. It's able to detect the difference between ints and doubles. So I'll just test this real quick. We'll say driver.display type. We'll do 123. And we'll do 3.14159. So we should get int and then double. Okay, so remember way back when I said all hard programs are made up of a bunch of easy parts? When we talked about programming languages, the difference between strongly typed and loosely typed languages. Loosely typed languages tend to also be interpreted languages, where strongly typed languages tend to be compiled languages. And related to that, compiled languages tend to be fast. Interpreted languages tend to be slow. One of the reasons they're considered to be slower is they require a type inference engine that sits there, and before you use any variable, before a variable gets resolved, it has to determine what kind of value lives in that variable so it can make sure that it's mappable, for example. Okay, you don't want to do addition with strings. Well, you can do addition with strings, but it's called concatenation. So you want to treat it differently. So this would be a simple little type inference engine. So when you call it a type inference engine, it sounds complex. The reality, it's something that just looks at the contents of a variable and makes it and distinguishes what's in there based on the different types that your language supports. That make sense? Okay, well, this would be a very simple one. So realistically, it would be more complex than this if you were to write one for like Java, but not substantially more complex. You couldn't really tell the difference between a double and a float unless the number was too big. But you don't really need to know the difference between a double and a float. You just need to know if it's a number, and if it's the plus sign that you're working with, is my result going to be a floating point value, or is my result going to be a integer value for math? Correct? If you're dealing with chars, then you're going to treat the plus sign as still math, but a step through the Unicode character stat. So that's what a type inference engine would do. All right, so we're going to say that we are good here on our reverse Polish calculator because we want to move on to something more difficult. All right, so I'm going to close all these. All right, now, how many of you have ever played the game Towers of Hanoi?
We talked about it.
Huh?
We talked about it.
Yeah, we talked about it.
We didn't write it though, right? Okay.
Well, we started to, and then we got sidetracked.
That was game
Yeah.
salad.
Yeah,
That was in Game Salad.
Oh,
Yeah.
they all go together.
Forget about that.
It was one of the classes. I don't remember what.
All right. So here's an example of Towers of Hanoi. Here, I'm going to reduce the number of rings to 3. All right. Well, that's pretty common. It's 3 rings. So can I start playing now?
You know,
Oh. Okay. So the goal is you want to get this stack in its current in its current state all the way over in the far right post. Okay. This is a stack. This is a stack. This is a stack. Now the rules of these stacks though is that a larger disk cannot go on top of a smaller disk. So if I go here and then I try to put this guy on top, it's an illegal move. So I can move him here. Then I can move this guy here. That's a legal move. Make sense? So that's how you can play the game. So what we want to do is we want to write a representation of this game using our stack data structures. But we need to create a stack data structure. Maybe we call it a tower. Okay? I.e. Towers of Hanoi. So a tower is a stack, but has a rule that pushing something onto the stack is only allowed if the value below, well, the current value on the top of the stack is smaller, or I'm sorry, is larger than the value you're trying to push on. Okay? So we need to create that version of a stack. So it's kind of a specialized stack. So let's go into here. We're going to create a new project. We'll call this CSC300 Spring 2015 Towers of Hanoi. We'll go ahead and create our new class driver. Okay, so there's our driver. Should be fully working. So now we want to go ahead and we want to create a data structure for tower. Now what is a tower? So we want to design this object. So a tower is a stack. Push is only allowed when the value being pushed is smaller than the value at the top of the stack. Okay, so it's a conditional push. We're only allowed to push if the value on top of the stack was smaller. So we probably want to have our push return a Boolean, letting us know whether it was allowed or not allowed. That make sense? Historically, we've had our push return a void, because pushing was just a movement, not anything that we expected to get something in return for. Okay, so we'll go ahead, we'll create our tower. So we're going to need a new class. Call this guy a tower. All right. Now, what's a tower? Well, a tower's got to keep track of the top of the stack, so a node. Now, the reality, though, is that our stacks are a collection of disks. So instead of a node, we have a disk. Okay? So we're going to create a disk class. Is it like that or like that?
I think it's a C.
See? Okay, so we're going to have a disk class, and what's a disk? So we go and look at this object, and we try to discern, what is this guy? How do we know that this guy is smaller than this guy, is smaller than this guy, is smaller than this guy? There's a value associated with it, right? Okay, so maybe we call that value size. Okay, so a disk has a size. So we'll call this guy like a node. Payload is an integer called size. Okay. And does a disk need to know about the guy that comes after him? It's still a linked data structure, right? So it's going to know about next disk. When we pop this guy off, we need to make sure that top becomes his new next disk. Right? So each disk needs to know about the previous guy because tower needs to keep track of the top of the stack. All right, so there's our tower. Now we need to create another class for disk. Okay, disk is going to have a private int size. It's also going to have a private disk next disk. We're going to have a constructor public disk takes in an int size, and we'll set this dot size equal to size, this dot next disk equal to null, and then we need to generate setters and getters. We want to have a get and a set for next disk, but we want to just have a get for our size. All right, so that's our current version of disk. So now we go back to tower. Well, a tower needs to know what the top of the tower is, so that's going to be a private disk top. We create our constructor for tower, public tower. Initially, it's going to have no disks in it, right? So we're going to say top is equal to null. Okay. Now we want to have the equivalent of a pop and the equivalent of a push. So a pop, we could call it pop if we want, or we could call it add disk and remove disk. Whatever makes us happy. Make sense? So I'm going to say, let's go ahead and say add disk is going to be something that returns a Boolean, add disk, and this guy is going to take in a disk as a parameter, which is a little bit different than what we've done before. Historically, what have we done? We have taken in integers and created the node inside of here and then pushed it onto the stack. In this case, we're actually moving physical disks from stack to stack. So we don't want to have to keep taking a disk, bringing it out here, destroying it, getting its value, then pushing it here. We want to be able to move things around as their full object, which is a disk. So we add a disk to a tower. Make sense? All right, so we're going to add a disk to this tower, and this guy is going to return, and I can make them public if I want. This guy is going to return true if we were able to successfully add this disk, and false otherwise. All right, so what does it mean to be able to successfully add a disk?
It's a legal move.
Okay, it's a legal move, and what does it mean for there to be a legal move?
The higher disk isn't going on top of a smaller disk.
Okay, so the trivial case is what if we're dealing with the empty stack? That is, what if this dot top is equal to null? Then we can definitely add it, right? We'll say top is equal to D, return true. Make sense? So if I have the empty stack, if my tower has nothing on it, it does not matter what kind of disk I'm putting it on there. It's legal. I can legally add a disk to the empty stack. So if top is nothing, go ahead and set top equal to the disk I'm adding and return true. I was able to successfully add it. Otherwise, if it's not the empty stack, I know there's at least one thing on the stack, and I need to look at it. Okay? I need to get the size of the top of the stack. Okay? So we need to be able to add a couple other features here. One of them is peak. Okay, we really haven't had to use peak very often before. So I'm going to go ahead, I'm going to create my function public disk peak. Okay, and this guy is going to return top. It's not removing it. It's not doing anything permanent. It's just giving us access to the top of the stack. That make sense? That's all peak does. Sometimes that's going to be null, so we'll have to take that into consideration when we're reading it here. But we happen to know if we're here, if we're in this else, that we know that peak must be something, must return something, because we're not dealing with the empty stack. Make sense?
Don't we want an else though?
Yeah, I will. I'll put it in there. Okay, so it's either the empty stack. I mean, you don't have to do it as an else if. You could just save an else and put an if in here, but whatever. So if it's the empty stack, go ahead and add the disk, return true. Otherwise, if d dot get size is less than this dot peak dot get size, it's a legal move, right? Now we could have just looked at top, but I really wanted to give us that opportunity of seeing where peak can come in handy. All right, so if the size of the disk we're trying to add is less than the size of the disk that's currently at the top, then we'll go ahead and allow it, correct? So what will we do? We're going to have to update things. So we're going to say d dot set next disk to top, and then top is equal to d. So make d point to the same place top points to, and then make top point to d as the new top of the stack. And then we will return true. Otherwise, and we didn't even need to put it in else, we're going to return false. Not allowed. Make sense? If it's the empty list, we're going to allow it. And trivially add it. Or the empty stack, rather. If it's a stack that has something in it, but the thing we're trying to add is smaller than the thing that's already at the top, then we'll go ahead and link it into our stack. Otherwise, not allowed to do it. That makes sense? Okay. And we're not even going to remove disks yet. We want to just test this logic. So I need to be able to display my stack. Okay. So I'm going to go ahead, or display my tower, sorry. So I'm going to create a public void display. And what this guy is going to do is he's going to go through and show the current state of my stack. Okay. So I'm going to walk from the top of the stack to the bottom of the stack, showing the size of each of those elements. Correct? Go ahead.
We need an is
Well, maybe. Depends how you want to do this. So displaying this, displaying our stack is going to mean what? I need to traverse our stack from top to bottom, right? Now, if we want to use this guy as a stack, we're probably going to do the is empty and then keep popping stuff off the stack and adding them to another stack, right? But we currently don't have a pop. So using only what we have right now, I'm not necessarily arguing that it's the the best way to do this, but we solve problems in terms of the tools that we have available to us. So using only what you know now and what's given to us here, I want to write a self-contained, so everything needs to go inside of display. No additional methods are allowed to be written. I want to write a version of display that will show the contents of this tower. So if there is a disk that's size 1, 2, and 3 in there, I should see a 1 with a 2 and a 3 underneath it. How would you write that? Using only what's in our class right now.
Using peek and get next disk.
Okay, well I don't have I get next disk, yes. So why would I need to use
To get the top of the
peak? Okay, I could use the peak to get the top. So if top is not equal to null,
So while top is not equal to null,
okay. We think back to our linked lists. Remember when we had our cur node, our cur disk? We had something point to the same place. So we might say disk temp is equal to, here, let's say disk cur is equal to this dot top. Okay, but before we even do that, if we ask the question if this dot top is equal to null, we're just going to do a system.out.println empty tower. Okay, so if we're dealing with the empty tower, just print out empty tower. Otherwise, we're going to go through this tower. So we'll set disk cur equal to the top. Then while cur dot get next disk is not equal to null, what will we do? We're going to say system.out.println cur dot get size. Okay, now we have an issue. What if I'm dealing with the stack or the tower that only has one disk in it? It's one disk in it, and I'm making my cur point to the top of the stack, point to that one disk. Then I ask this question. Is there a next disk? Does the current guy have a next disk? It doesn't. So will I ever print this?
Isn't it just like in linked list where we had to end the while statement with another cur dot get size?
Well, we could. Could we also write this using a do while loop? Do we know for a fact, if I'm in this else, that I'm going to have to print out once?
Yeah.
I know that for a fact, right? Now we did forget something here. We said cur dot cur should be equal to cur dot get next disk. All right. So we could do this as a do while loop, or could we just say this? While cur is not equal to null. We know if we're in here the very first time through, it won't be null because we checked for the null right here. So we'll set cur to the actual top of the tower as long as it points to something real, which we know as a human that the first time through it will. We'll go ahead and get the size, print it, and then set cur equal to the next disk. Then loop back up. Okay? But now we are asking a question here when we know we don't have to ask that question as humans. So I'm going to steal that. So I'm going to say do this stuff and keep doing it as long as cur is not equal to null. Right? If I'm in this else, there's at least one thing in our tower because I checked to make sure our tower was not empty. So if I'm in this else, I'll set cur equal to top, print out top, set cur equal to cur's next disk, which might be null. While cur is not equal to null, spin up and do it again. Otherwise, we'll fall past it. Make sense? This is from an efficiency perspective, this is a reasonable use of a do while loop. Even though we can certainly do this as a while loop. That gets back to our original discussion back last semester about how do each loop lends themselves to different types of problems, and a do while loop lends itself to problems where we need to do something at least once. Well, here's a situation where we have to do something at least once. Have to display at least one disk. Okay? But any problem that can be solved using loops can be solved using any of the loops with the right amount of asking questions and some other stuff. Make sense? So this saves us from asking one question, guaranteed every single time through. Again, not the end of the world. Asking to see if cur is equal to null or cur not equal to null isn't going to take up that much CPU time. We wouldn't even notice, but if we're looking for a reason to use a do while loop, this would be a realistic reason to use a do while loop. Make sense? So not something we see that often, but reasonable in this case. So to display our loop, if we have the empty tower, we'll just show it. Otherwise, we'll spin through our tower. We have not broken our tower at all. We haven't removed anything. We're not even using the stack functions. We're just taking advantage of the nature of disks. Okay? And we're walking through showing each size. So now out here in driver, let's add a couple of elements. So I'm going to say tower t is equal to new tower. So I just use our constructor that takes no parameters and sets top equal to null. Now I'm going to start adding some stuff to our tower. So I'm going to say t dot add disk, add a new disk of size 1. Then I'll say t dot add disk, new disk of size, we'll make this one 0. T dot add disk of size 5. Then we'll say t dot display. So we're going to try to put a 1 on top of the empty tower, which will be allowed. Then we'll try to put a 0 on top of a 1, which will also be allowed. 0 is smaller than 1. Then we're going to try to put a 5 on top of a 0. It's not going to allow it. So when we display this, our tower should look like a 0, then a 1. So there's our 0 and our 1. Make sense? Okay. And these guys were giving us answers as well. So I could have printed these out, system.out.println. And we would be seeing trues and falses coming out of our adds. So this would be true, true, false before we ever display. True, true, false. I was able to add, I was able to add, this didn't work. All right, make sense? All right, so now we have a tower that functions the way it's supposed to function in terms of putting stuff on to the tower. So we're in the middle of building a tool that we can then use. Okay, so we know now we have a tower that we can't force disks onto that shouldn't be allowed. So now we need to be able to remove a disk from a tower. So we're going to say public Boolean remove disk. And remove disk is going to say if, I'm sorry, not Boolean. Public disk remove disk. And we're going to return this dot top ultimately. But I need to adjust my stack, correct? I'm physically removing this from the stack. Physically removing this. So before I can just return the top, I'm going to say disk node to return is equal to top. Then we're going to say top is equal to top.getNextDisk. So that sets the top to the new top, which might be null. Make sense? So I'm going to preserve the disk I need to return. Then I'm going to set top equal to the new disk. And then ultimately we will return node to return. So that's how remove disk works. Now we know whether or not a disk was successfully removed as long as whenever we call this, we don't get a null. Okay, and let me show you that. So we'll go back out here to driver. We happen to know after these 3 lines, 2 disks are on our tower, right? So what I'm going to do is I'm going to say system.out.println t.remove disk. That'll remove 1. That'll remove 2. That'll remove 3. Or the third one's not there. What's the output of this program going to be? We already had our old output, right? True, true, false, and then 0, 1 for our display. What's the output down here going to be? Be a good quiz, isn't it? Oh, by the way, so I don't forget, I did get your email. I'll reply to it soon.
Okay. I was
But it was received. We'll figure something out. No takers?
I'll go 0, 1, null.
0, 1, null. Okay, tell me why he's wrong. Everybody in here should know this.
No, 0, 1, no pointer exception.
Okay, no, still wrong. And as soon as he hears the answer, he'll know exactly why he's wrong. It's just having a brain fart. Fell for my trap. What gets removed from remove disk? The disk. This is just a reading exercise. We're not programming at this point. It's a reading exercise. So remove disk ultimately produces for us a disk. What kind of animal is a disk? It's an object. Objects hold pointers. This is a memory address. So what will the output of this be?
0, 1 memory address.
All right. Somebody tell him why that was an idiotic statement.
What he said.
He said 0, 1 memory address.
It'll be memory address, memory address.
Well,
No pointer exception.
That's right.
well,
Except it will be null.
I wasn't stopping there.
You just. Yes, you were.
Which one?
All right. So this guy actually removes a disk. We're displaying that disk. It's going to display a memory address. This guy actually removes a disk. It's a real disk. It's going to show a memory address. This guy tries to remove a disk, and it's going to get a null value. It's going to get the current value of top. Correct? Okay. So it will return a null value. Go back in here to tower. We look at remove disk. We get top, so node to return, and then we set top equal to tops get next disk. All right. Okay, now I'm still trying to trick you. Will this guy get a null? We will get a null pointer exception, but not because of this. We get a null pointer exception because of this. If top is null, we're going to get its next, we try to get its next disk. So if I say top not equal to null, I like saying this dot top, just be explicit. So if this dot top is not equal to null, then we know we need to update top. Otherwise, we're just going to return, well, in any case, we're going to return node to return. If this was already the empty stack, we don't need to update anything. We'll just return what top used to be, which is null. So that'll be a null value. Okay? So now we won't have a null pointer exception. Instead, this guy boils down to null. What prints out when we try to print a null value? Is that a null pointer exception to print out a null value?
No.
Just says null. So memory address, null. So to display a null value, it prints out null. Now the question here is, t.remove disk, that printed out null, correct? Does that mean that this should be true?
It's a string equivalent of null.
String equivalent of null? So this would be true? Okay. This guy's a disk. This guy's a disk. And when we print out a disk, what do we get? We get that disk's, the result of that disk's toString method. The result of that disk's toString method. So now this will boil down to its value. Its value is null. I'm saying is null equal to null, so this will print out true. But when I don't have the double equal sign here, I just have that. This value boils down to what? The result of t dot remove disk, which is a disk, dot toString. Which gives us why I get a null pointer exception.
You're trying to take it to the string.
Trying to call toString on a null value. So this is not even a real object. It's not a disk. It's nothing. It's nothingness. Right? So we are seeing a special case for null objects. There's a version of println that takes an object as a parameter. And if that object has a real value, it calls that object's toString method. If it doesn't have a real value, it displays the string null. Make sense? And just to show you how that toString thing works, and this goes back to us making this work like he originally said he wants it to work. We're going to go, so right now this is going to be memory address, null, correct? So memory address, null. Because this guy's a disk and this guy's a disk. And disks all extend object. So that means every single disk gets their own version. Gets their own version of the toString method. Okay? So I just used the thing that makes invisible ink show up. So this was already there, but now we're seeing it. So the output of the program is going to still be the same. All right? And what I'm telling you is down here, we have a toString method. And this guy returns super.toString. And this guy probably needs to be public. All right, so we inherited this method. Okay, so I'm kind of showing you that it's there. So we got a method called toString that came from our parent, and at the parent level, this guy just printed out itself, whatever its toString does. But I'm going to rewrite the toString method myself here, and I'm just going to say do whatever the parent says to do. Kind of a wasted method. I'm just passing the buck. Okay, you want to call my toString? Sure, I'll just call my parent's toString and have it do whatever it was going to do. This would have automatically happened had we not written this. So we're going to see our output is still the same. Same output, because we're calling upon our parent's toString. But now we're going to say, you know what? Instead of calling upon my parent, what I'm going to do is I'm going to say return the string version of this dot size. Now we get 0, 1, null. So there's our evidence that the println method is calling the toString method of the object that it's passed. Okay, we really want the memory addresses as well. We can say I'm going to return a string that is the empty string concatenated with the size, concatenated with maybe an opening parenthesis, concatenated with super.toString, concatenated with a closing parenthesis. So now it'll be the size with the memory address in parentheses. Because this toString method returns a string representation for an object. So I'm going to say the string representation of this object, this disk, is going to be its size followed by opening parenthesis, followed by whatever the parent's toString method returns, which we know in this case is a memory address looking thing, followed by a closing parenthesis. So now we see we get the size followed by the address, the size followed by the address. Make sense how toString works? All right, so for your homework, what's up? You want homework?
No.
You don't want homework?
When's the midterm coming up?
I don't know, but that has nothing to do with our homework. Okay, so for your homework, I'll make it an easy one. Okay, so we've seen how this stuff works. So for your homework, I want you to create something similar to our little calculator, which gives us a little prompt that asks us what we want to do. And I want you to have two towers and be able to say remove from a tower and add to a tower. So she asks you two questions. What tower is the source? What tower is the destination? So if I say the source is tower 1, destination is tower 2, it should pop off tower 1 and push on to tower 2. And then you'd be able to use the display method to see that it worked.
It's like how would you display that though? Is like two towers?
Yeah, just two towers, one after each other, just knowing that the first one is the first numbers and the second one is the second numbers. You know, you can decide inside your tower that you want to put, some, like divider in there or something like that. All right, I'll put this code up as a starting point. And I'll give you a little example of what I think it should look like, just as as a starting point. So really, you're taking what you did from the reverse Polish assignment, where you have your little prompt, and all you're doing then is just using our towers that we just built. Make sense? All right, I'll see everybody on Thursday.
When's the midterm in this class?
When's week 8?
After spring break?
Is it? No, I'll probably do it before spring break.
So next week?
Is that next week?
Yeah.
Yeah, so ask me on
Thursday?
Thursday. We'll probably do it maybe on the Thursday right before spring break. That way nobody skips.
We can just do it on Tuesday and then cancel
Huh?
class on Thursday, so you get all.
That sounds brilliant.
That sounds like a great idea.
What's this?
Said we do it on Tuesday and then just cancel class on Thursday.
Oh, we got so much stuff to get through. We'll never.
Spanish teacher did.
Well, Spanish is easy.
Do it on Wednesday and then cancel.
There's
on
so
Friday.
much content in here. We're always behind. Won't you feel cheated? I mean, you're paying top dollar for this education.